Cool, thanks. Thank you for the invitation. Please feel free to turn your cameras on. I may put like another computer next to me so I can see people's faces, but in any case. So yeah, so this is about some work for my thesis. Yeah, okay, so let's talk. So okay, what we're going to do is we're going to start by thinking about just curves in projective space. So maybe I can zoom this in. Okay, so let's think about curves in projective space. So in PN, and so okay, so here's like three different perspectives. Okay, so the first one is okay, so I could think about a curve via like its equations, via the ideal. The second way I could think of it is via like a parameterization, via parameterization. And the third one is, because this is a parameterization, just a map to projective space, I could think about this via the defining kind of line bundle intersections. So okay, so because every map to projective space is just given by a line bundle and then n+1 sections. Okay, and these are for like smooth embedded curves, or just even more generally, these are just the same. These are just different perspectives, not really any difference. But 2 and 3 are like kind of like literally the same, but kind of in the world of modern curve counting, they give kind of different approaches. So okay, so what is the world of modern curve counting? So okay, so I'm going to tell you what the modern curve counting machine is. Okay, so how does the modern curve counting machine work? So what you do is you start off with this with some smooth projective variety, smooth, and what I do is I associate to it some space m of x, which is like curves in x. So this is some kind of space of curves in x. Some moduli space, and then I take this moduli space, and then I go and do some integrals over it. And these are called invariants, and roughly they should be thought of as counting curves in x satisfying some conditions. But in any case, this is the modern curve counting way. And so what happens if you take each of the three approaches on the first page to the modern curve counting machine? So okay, so the first approach gives you Donaldson Thomas theory. Maybe one more thing, like just so in order to go from step 2 to step 3, there are like two things you need. So I can't pass through the second arrow unless m of x is kind of proper or compact and smooth in some sense. But okay, so there's some restriction. But okay, but what are these three ways of thinking about curves in projective space? give you in the modern curve counting sense. Okay, so they give you Donaldson-Thomas theory, and then if I think about parameterized curves, that gives me Gromov-Witten theory. And then if I think about curves via the defining line bundle and section, what this leads to is Quasimap theory. Okay, so this is probably the kind of least famous of the three, but I'm going to try and like push it as hard as I can for this hour. So what are the moduli spaces? So okay, I'm going to ignore one from like now on. But for two, this is the moduli space of stable maps. So I added some numbers here. So the number G just means I'm going to keep track of the genus of the curve. Beta means I'm going to keep track of the degree of the curve. And N just means I'm going to keep track of like a bunch of points on the curve. So I'm just gonna like mark them. Okay, so that's what the numbers are, and then the moduli space for Gromov-Witten theory is called the moduli space of stable maps, and the moduli space for Quasimap theory is called the moduli space of Quasimaps. So that's okay. But I said before that like 2 and 3, a map to projective space is just a line bundle and a bunch of sections. So why are 2 and 3 any different? Why aren't they just the same thing? So how do 2 and 3 differ? So okay, so maybe I'll just write again. So this was there was some Gromov-Witten space, which was so it's a curve. So yeah, what is it a set of? It's a bunch of it's a curve, a bunch of points on the curve, and then a map from the curve to projective space. Okay, and then what's this Quasimap space? So it's also a curve, a bunch of points, but now I tell you a line bundle and a bunch of sections. So and we just said these are like the same thing, right? So how are these different? And so, but the point is that the limiting objects can be different. So the limiting objects differ. So in particular, in this Quasimap space, in the Quasimap setting, we can have base points. So what you do is you let these sections vanish sometimes, or simultaneously vanish sometimes. Okay, so maybe that was abstract. So maybe I'll do an example. So okay, so example is going to be okay. So I'm going to think of rational curves. So this G is 0. We're not going to bother with the number of mark points. We'll go to P2 and let's consider degree 2 maps. Okay, and okay, let's versus the corresponding Quasimap space. Okay, so if I give you any non-zero complex number, I could write down the following map, which is just P1 goes to P2, and it maps in homogeneous coordinates. It maps Z0, Z1 to T Z0 squared, Z0, Z1, Z1 squared. Okay, and this is this gives me a perfectly good, this gives me a perfectly good degree 2 map to P2, right? This is a, and okay, but equivalently, I could regard it as P1 together with the line bundle O of 2, and then the sections T Z0 squared, Z0 Z1, and Z1 squared. Okay, so these are like the same, but this I'm thinking of as as a Quasimap. Okay, but what happens? So the question I want to ask is what happens as t goes to 0? Okay, so if I just setting t equals 0 gives okay, so this gives me this thing, but this is not defined everywhere. So if z1 equals 0, this isn't defined. So not defined at 1, 0. But on the other hand, on the other hand, this kind of curve, line bundle, and triple of sections are perfectly valid in this Quasimap setting. So this is okay. So this is oops. So this is the limit in the Quasimap setting. But what about the limit in this setting, this Gromov-Witten setting? Because before we said all of these moduli spaces are compact, so there has to be some limit. So okay, so I have some picture. So okay, so this is in the quasi. So when t is not 0, this is just like a degree 2 map from a smooth curve to P2. Okay, and then okay, so what's the, so when t is 0, what's what is this map? So okay, so the Gromov-Witten map is what you do is you map degree 1 here, but then you add in another component, and you also map it degree 1. But okay, and as we saw in the Quasimap limit, you also okay, so what you do is you have this map from a smooth curve to P2, but there's some base point which I've like drawn with like a white circle. So okay, just to summarize so far, I gave you like a bunch of different ways to think about curves in projective space. I kind of ignored the ideal one, but the two ones I wanted to focus on were kind of thinking of curves as maps to projective space versus thinking of them via the line bundle and the sections. And then I've said, in this world of curve counting, where we think about things in terms of moduli spaces, these give like two different approaches. And one of them gives you the moduli space of stable maps, which is some object in Gromov-Witten theory. And the other one gives you something called the moduli space of Quasimaps. And so Quasimaps because the map isn't like defined everywhere. Is that okay? Are there any questions so far? No? Okay. And so the only other thing I want to say about this is that I want to like push the agenda that the Quasimap space is like better. So is so that I want to say the Quasimap space is a kind of more efficient compactification. And so what I mean about this is that if we compare these two limits, there are a bunch of different stable maps where I can choose where this red curve goes, and I just have to insist that it passes through the node that connects the blue and red curve. But I can just define it to be any line in P2 through that point, and so that gives me some moduli, which makes this moduli space bigger. But the Quasimap space, I have like nothing else to choose once I've picked a base point here. So that's some like rough reason for why the moduli space of stable maps is like bigger than this Quasimap space. Okay, so maybe some just like summary. summary guide to Quasimaps. So if X is, we focus on projective space, but whenever X is like a nice GIT quotient, maybe like a toric variety or something, then you get some moduli space of Quasimaps, which is proper. And it's also, there was some smoothness condition. It satisfies the smoothness condition. And the kind of cool thing about them is that because they're kind of smaller than the Gromov-Witten space, they're like invariants are like easier to compute. So Quasimap invariants are like easier to compute. And and kind of moreover, there are like wall crossing formulas. Which relate Gromov-Witten invariants and Quasimap invariants. So if your life revolves around computing Gromov-Witten invariants, this is like good news, because this gives you some kind of like two-step procedure for computing Gromov-Witten invariants. What you do is you like go and compute the Quasimap invariants and then use some wall crossing formula to get from one to the other. Okay. So that was my like kind of quick fire summary on Quasimap theory, and now I want to talk about, so that the title was like logarithmic Quasimap, so now I want to like get onto that part. But are there any questions? Okay, so so before we were talking about were curves just in some projective variety, so just some like projective space or something. But now what I would like to do is I'd like to fix not just X, but also D, some divisor. And now what I would like to do is, now I'd like to think about not just curves in X, but curves in X which are like tangent to D in some specified way. Curves in X with fixed tangency to D. So before we were thinking about conics in P2, and now I'm saying think about like conics in P2 tangent to a line, tangent to some fixed line. Okay, so now I would like to try and play the same game and see if I can see if there's another moduli space that's proper that compactifies these objects. So how do you build an appropriate moduli space? Okay, so there's some problem. So what I want to imagine is that like generically I want to, so this is supposed to be a picture of, so in black that's my divisor and the blue thing is my curve, and I want to say that generically I can just specify my tangency and insist that it hits this hyperplane with contact orders 2. Let's say this is like 2 here and 3 here. And the problem is this space is not proper. Like if in the limit, what can happen is this whole curve or components of it can just fall into this divisor, and then I don't know what tangency means. So the space. So the space of curves in X tangent to D with like specified contact orders is not compact. Okay, so yeah, example. So kind of similar to the one we saw before, if I just give you, maybe I'll say, so consider as t goes to 0, the following map. So now I send z0, z1, so this is on P1, to t z0 squared, z1 squared, z0 squared. Okay, and so this is in P2. And so, and let's let d be the vanishing of the first coordinate. So when t is not equal to 0, this just looks like what we saw before, which was just a smooth curve mapping into P2, and it had like quadratic tangency at the point 0, 1. But when t equals 0, this thing just falls. This thing just becomes a degree 2 cover of the line given by x0 equals 0. So at this point, I don't know what tangency is, and so I need to think of something else. So in the Gromov-Witten setting, so this parameter, when you think of parameterized curves, there've been like loads of different iterations of solution to this problem. So there have been many solutions, and kind of the most general one, which is due to Abramovich, Chen, Gross, and Siebert, uses logarithmic structures. So it's okay. It's not important what this is. It's just this is just extra data on the curve and the target, just so that I can say what tangency means, even in this situation or this situation. So you can say what tangency is in the limit. Okay. So now I want to tell you about this kind of Quasimaps for just like a variety and a divisor now. So there's some kind of simpler solution due to Battistella and Mabijou, following some idea of Gutman, where you say, okay, well, I just have I have my space of curves which is like non-compact, like they look like this, and they live inside a compact space, which is just the ordinary Quasimap space, and I just take the closure. So take the closure of the locus with kind of correct tangencies in the kind of ordinary space. Which works, but it's kind of restrictive. So it works when the curve is rational and D is smooth and very ample. And so what I'd like to do instead is instead I want to kind of utilize this modern solution of attaching this extra data to the curve and target. Utilize the modern solution in Gromov-Witten theory. Okay, so but first maybe I'll just kind of say something about like what tangency is. So okay, so what is tangency? So okay, let's just say I have a curve and a point and a map to x, and I care about tangency to some divisor d. And let's say SD is the local equation that cuts out d. Okay, then what does it mean? What is the tangency at P? What does that mean? So tangency at P, what that means is I take the equation that cut out D and I pull it back to the curve and see to what order that vanished at P. So it's the order of vanishing of the pullback of the equation that cut out D at P. So okay, so example for this one we gave, so P1 0 1 goes to P2 with the divisor given by the first coordinate vanishing, and the map was the one we said before, which goes to Z0 squared, Z0, what do we say, Z1 squared and Z0 squared, then this thing just has tangency 2 because the pullback of the equation for x0 is Z0 squared. So it has tangency 2 at the point 0, 1.
Can I ask a quick question?
Yeah, absolutely.
So, oh, hey, by the way. If you take like one of your Quasimaps, so you think of this as some like map from your curve, but it also has base points, right? Because the sections can.
That's right.
So you can't talk about for order of tangency in this sense for base points. Is that correct?
That's correct. Yeah, that's right. Yeah, yeah, that's right. Okay, maybe I'll just. Yeah, that's right. There's no well-defined notion of tangency at the base point, but what I was about to say is that it's fine. There's a tangency everywhere else.
Okay, thanks.
I mean, there's not even a map at the base point. So, so yeah. So as Robert says, so for Quasimaps, there's no map. There's no map that like there's no map like this, but we still have kind of the moral pullback of this equation. So we still have this like line bundle and section pair on the curve. I guess this is like U0 on the curve, and so tangency at P is just the order of vanishing of this section at the point P. And yeah, as Robert said, you know, you can't ask this at a base point because a base point is where this section and indeed all the others vanish. So it doesn't make sense to ask what the order of vanishing is at that point. Yeah, thanks for the question. But kind of we have basically the same problem. So the same problem, which is that, you know, in the limit, this section could just vanish on whole components of the curve or even the whole curve itself. And so kind of, and you know, and then, you know, you could think the order of vanishing then is like infinity or something. And so, okay, what I'd like to do is I'd like to use this this idea of putting log structures on both the curve and the target to solve this problem. So I want to endow C and X with log structures. So this is just some extra data to keep track of this. But the problem is there's no map. So there is no map C to X. So okay, maybe to tell you what to do instead, I'm just going to use some analogy. So okay, here's a fact/analogy. So a map from a curve to A1 is, by definition, the same thing as a regular function on the curve. Okay, and we don't have a regular function. What do we have? We have like a kind of line bundle and section. And okay, that's not the same thing as a map to A1, but it's the same thing as a map to A1 modulo modulo C star. Okay, so I guess that's just like a definition. But the point is now, okay, whatever this thing is, now we have like an actual map. So now we have an actual morphism to put this extra data on. Okay, and so what I'd like to propose is that a kind of logarithmic or relative, these are like synonyms. Oops. Quasimap. I'll just say to Pn relative, and the divisor is just the first coordinate vanishing. Is okay. Well, it's just a Quasimap, so I have to tell you a curve, a bunch of points on the curve, a line bundle, and a bunch of sections. But maybe they vanish somewhere. Plus kind of logarithmic enhancement, whatever that means, of the map C to this quotient, which was given by the line bundle and then the first section, because that corresponded to the pullback of the equation that got out the hyperplane. And then such that this log map has the kind of appropriate tangency. Okay. So okay, if you do this, then this leads to some solution to the problem. So then if some generalization of this says that if X is a smooth projective toric variety and D is a simple normal crossings divisor, and G and N are integers, beta is a curve class on X, and alpha ij is some contact order data. Then okay, there exists a moduli space parameterizing kind of log Quasimaps, which is proper. And kind of moreover, this moduli space is virtually smooth. Okay, and then kind of also just the kind of the numbers you get out of this. So okay, so once you have your moduli space, do you remember the game? I give you my variety and a divisor. I give you a moduli space, and then I do some integrals over it. And the integrals you get, so the invariants agree with the kind of previous solution to this problem with the invariance of Bastana and Abajou for G is 0, D smooth, and very ample. Okay, so I'd like to still push the case that this space is like simpler than the Gromov-Witten space, although I realize that maybe people in the audience don't have kind of experience with kind of either context. So I have made a table to push my case. So okay, so logarithmic or relative Quasimap spaces are also kind of simpler than their Gromov-Witten counterparts. And so I have hopefully hidden below a table, which maybe I can drag up. Oops. Okay. I thought this would be smoother. Okay, so here's my table. What does it show? So okay, the simplest possible case you could imagine is having genus 0, projective space as your variety, the first coordinate vanishing, which we've been using this whole time, as being the divisor. So that's H. Sorry, H just stands for hyperplane, which I guess I called D earlier. There's okay for Quasimaps, you actually have to have 2 markings to have anything. And this is the number of boundary divisors. So the space, both spaces are actually irreducible, but they have differing numbers of boundary divisors. And so I've written the number of boundary divisors for the Quasimap space and the corresponding Gromov-Witten space. And so this is supposed to be my like propaganda for why the space is like in some sense better behaved. Okay. Do people have any questions?
Yeah. Is it true that number of boundary divisors is always less than, lower than the case of the moduli space, like the Quasimap case, or is that just a special?
Yes. So it's always true, but I kind of, as part of my propaganda, I picked the example that exaggerates it the most. So somehow the more mark points you have, the less opportunity the Quasimap space has to save components.
Okay.
But yeah, thanks for the question. So yeah, so the answer is yes, but this is like the most extreme case. So okay. So okay, so the last thing I'd like to do is just say something about what is it good for. So what is, so you know, I've spent the last 40 minutes telling you about something called logarithmic Quasimaps, but you know, maybe you're like, why? But you, okay. Okay, so why? So I'm gonna, so two reasons. So okay, the first reason is going to be some kind of wall crossing in this context. So earlier I said there was some kind of good way to compute Gromov-Witten invariants, which is compute the Quasimap invariants and then use these wall crossing formulas that were proved. And so I want to give some evidence that there should be like a kind of analog in this case of these wall crossing formulas. And the second one is something called the local logarithmic correspondence. Logarithmic correspondence. So okay, so the first one. So Fan, Seng, and Yo show there's a generating function for kind of relative Gromov-Witten invariants in genus 0 can be obtained via a kind of change of variables, which I'm going to suggestively write below wall crossing question mark. Change of variables from something they call a relative I function. Okay, so okay, that's one fact. On the other hand, in this kind of first iteration of the solution to this Quasimap problem, Batista and Abajou show that that their relative I function is a generating function of kind of relative Quasimap invariants. Okay, and so this is supposed to be like evidence, or maybe hints at evidence for wall crossing, kind of in more generality in this context. Okay, so that's the first thing, and then the kind of final thing I wanted to say was this second point. So this local logarithmic correspondence. So okay, so Vangaro, Graeber, and Rudat show so that, okay, I'll write it and then let's show that the kind of maximal contacts log or relative invariants coincide with something called local invariants. So just to explain this, on the one side we have, so this is log and this is local. So log means I take x relative my divisor and I consider one marking with like maximal tangency. So if I concentrate all the degree to just one marking and it only intersects the divisor at that point and it's as high as it could be. So if I did degree D maps to projective space and a hyperplane, I want like contact order D at the marking to the hyperplane. Okay, so that's one thing. And then on the other hand, you could consider just kind of ordinary Gromov-Witten invariants of the total space of this bundle, like no log, with no markings. And these things are actually equal, so the virtual classes are equal up to some constant. So so this is really cool, and they conjectured a generalization for when D is not like a smooth divisor, but when D is like a sum, like a reducible, like a simple normal crossings divisor. And kind of, this kind of, although this holds in cases, so there's some work of Bousseau, Rini, and Vangaro, the kind of analog, of the kind of full conjecture is kind of false, and so there are like some counterexamples due to Navajou and Ranganathan, and the kind of interesting thing about them is the kind of correction terms basically involve so before I showed you there were, the difference between these two spaces, there was like loads more boundary divisors in the Gromov-Witten space. They kind of include the components which wouldn't or are less likely to appear in the Quasimap setting. So speculation, maybe the generalization holds for Quasimaps. So this would be cool because if you do both of these things, then on the one hand you can relate relative Quasimap invariants to relative Gromov-Witten invariants, but then maybe you could compute the Gromov-Witten invariants via this correspondence, because there are like localization techniques over here that kind of don't work, that aren't over here. And so combining these could be quite interesting, but most of this section was kind of like speculation. And so yeah, that is where I wanted to end. So thanks for listening to my talk, everyone. Do you have any questions?